下面我们邀请这个来自这个安德里茨水电产品，他经理叫布鲁诺梅拉奇先生发言。他发言的题目是泵作水轮机的应用。那么应该说，这个安德里茨水电产品呢，也是全球比较知名的一个水电设备供应商。下面大家欢迎。
Thank you for the introduction. Welcome here to this very beautiful organized event. Dear ladies and gentlemen, dear guests, I have the pleasure to introduce the company Andritz briefly to you, and also our special technology, what we also use is reverse running pumps used as turbines. My name is Bruno Mellacher and I'm working in Austria, in Graz, in our headquarters. So, Andritz is a global leading supplier of production systems for selected industries like hydropower, for pulp and paper industry, for metal and solid liquid separation. We are an international group. We are having an order intake of roughly 6 billion euros per year, and we have all over the world around 25,000 employees, and we have 250 production sites all over the world. We are organized in 4 different independent divisions. One division is the hydro division, where we are specialized in hydropower generation. Andritz is the world market leader in hydropower generation. Then we have the second, nearly same size division for pulp and paper, where we supply paper machines and also turnkey pulp lines. Then we have the metals division, where we produce strip processing lines and stamping machines for the automotive industry. And our smallest division is the separation division, where we are specialized in separating solids and liquids. Inside the hydro division, we also have some organization. There we have the large hydro division, where we can supply turnkey large hydro plants for hydropower generation of the biggest size. Then the smaller ones up to 20 megawatts we call the compact hydro turbines. Then we have the service and rehab division, where we do the service of large hydropower stations. Then we have the pumps department, where I come from, where we do some engineered pumps and also standard pumps. And then we have the small division where we produce turbo generators for gas-fired power stations. Our pumps that we produce can be used in different industries. This could be in the power industry as intake pumps or cooling water circulation pumps, for the water supply and distribution, inside industry for pulp and paper, sugar, starch or other industries, in mining and also for offshore applications. So now we come to the details about the reverse running pumps as turbines. These pumps, these turbines, are for micropower stations a very efficient way to generate power. And I will show you in detail some applications, the performance range, design and function of the pump as turbine, advantages and also some references. Here you see the overall picture, the field where we can use our pumps as turbines. Basic performance data could be, the pumps could be used, standard pumps, single stage pumps and also double suction pumps for a head up to 80 meters, and the flow is up to 800 liters per second for end suction pumps and up to 6 cubics per second for double suction pumps. And with multi-stage pumps, we use them up to 350 meters head, and the flow is from very small, roughly 25 liters per second, up to 250 liters per second. Oh, sorry. So now, possible applications that we have, and I will show you some references for each application. We have supplied island power stations for mountain refuges, which are working completely independent in island mode. Also some drinking water turbines and drinking water systems. wastewater turbines, where we use the remaining head of wastewater. Residual flow turbines for the ecological flow of hydropower stations. Then we have some micropower stations which supply to grid. We also can use some energy recovery turbines in industrial applications. And we also have the possibility to provide some small pump storage power stations, which we would like to realize somehow. So here you see the overall working range of all the turbines which there are. If you start from the right below corner, there you see the bulk turbines, which are designed for very low head but very big flow. And then you come to the Kaplan turbines and the Francis type turbines and engineered large Pelton turbines. And now in the left upper corner there are the standard Pelton turbines. And then on the left lower corner you see the applications with pump-based turbine and also hydrodynamic screw. So we are in that range where we can produce an energy between 5 kilowatts up to, per single unit, some maximum 2 megawatt, which is possible if there's a constant flow and one constant head. Here you see the cross-sectional view of an end suction pump that we use. These pumps are coming out of the pulp and paper industry and they are very resistant. So for those pumps we have an open impeller, which is a non-clogging application. There is the front and rear wear lining, and then we have the pump casing itself and the bearing unit. The same view of a double suction pump. It shows that there is a bipartite spiral casing, axial slip case. The shaft sealing could be a stuffing box packing or alternatively a mechanical seal. The impeller itself is a double suction impeller which is designed for especially low pulsation and that produces a very high efficient pump. And you have the shaft bearing unit. There are mainly two material versions that we use for those pumps. The one design is CD, where we have the casing and casing cover made from cast iron. This is the standard application for water. All other wet parts like impeller, front, rear wear liners and also the shaft are made from duplex stainless steel. And the design DD, where we have also the casing and casing cover made from duplex stainless steel. The multistage pumps, they are designed for water applications, so that means the casing is made from cast iron, the impellers are also made from bronze, the bearings, diffusers are made from cast iron, and shaft and sleeves are stainless steel. So now what are the advantages of pumps used as turbines? As I mentioned before, these pumps, they are very resistant. They are used to work in industrial applications where they need to be very rushed and should have good service life. Because of this design, they also need only little and easy maintenance. The impeller is open with large free passage and low problems with clogging. We could connect the generator direct or by belt drive, gearbox, if there is a different speed between generator and pump required. These pumps are coming from serial production, so that means they have short delivery time and they are also cheap compared to real turbines. Pumps as turbines are working as non-regulated turbines. So that means they have one disadvantage. They have only one optimum duty point. And this duty point we try to meet by our philosophy that we use them only in applications where the pump fits perfect as turbine. So we do a very careful selection of the unit. So the comfort possibilities of a pump as a turbine, since the casing is working as a rigid guide vane, and there is, as I mentioned before, only one optimum duty point. You see here one example duty point in the middle of this left-hand side picture at the head of 45 meter and a flow of 150 liter per second. And there the duty point meets the turbine curve of the pump. If I now would have an additional surplus flow, this flow could pass the pump as turbine only if I would increase the head, which usually is not possible. So that means I need to have a kind of bypass or an overflow like there, where the water can pass. If the water amount now is reduced, the pump as turbine will not utilize all the available head. There would be some additional head available, which I just could use by throttling or just let the available pressure inside the system. This is the one possibility, the throttle control. The other possibility would be to run the unit with variable speed, and this variable speed would shift the optimum efficiency point. So in top of the left-hand side picture, you can see two red lines. The one line is showing the efficiency at 1,500 RPM, and left of it, the other line shows the efficiency with 1,000 RPM. So this is what we play with when we have a different head at an application. So now this is the overall system and the main components. Here you can see the pump as turbine itself. At the pressure flange, in front of the pressure flange, we connect the control valve where we can control the unit. And this control valve could use with a 24-volt DC drive for the flow control and the emergency shutdown. Then we connect the generator, which could be asynchronous type. Then we supply the power parallel to grid. Or we use a synchronous island-driven one. In that case, we would also suggest to use a flywheel to stabilize the frequency a bit. In our low-voltage switchboard, we have the current distribution, fuses, control unit, and also battery. The battery is in use that we can shut down the system when we lose the connection to the grid. This is another possibility where we have a pump as turbine in use, where on the tail race also would be some pressure available. At that application, we need some additional valves. We'll take a closer look here. So first we have at the entry side one manual valve for maintenance. This is for isolation. In between there's a dismantling pipe, and then we come to our control valve, which is electric actuated for the control. Then we have the pump as turbine, which also has the connection to an asynchronous generator in that case. And behind the turbine then is the manual isolating valve, which you also need to isolate in case you do some maintenance to the unit. Now I'll show you some applications that we have supplied. This one is very old. It is supplied 1984. This was the first pump as turbine that we have supplied. It is running in the Austrian Alps in an area where no connection to the grid was possible. And this is in use from a small cottage which is in use as a restaurant. This unit is producing 18 kilowatt and it is still in use, it is still operating after such a long time. I visited it just 2 years ago. Another very typical possibility to use pump as turbine is the multistage pump as turbine. And here we take a look on the run-out characteristic of a pump as turbine. So the pump as turbine is running at the speed of 1,500 RPM in this example and meets the plant curve. And in case now the unit is losing the connection to the grid, the generator loses its load. And in that case, the speed of the unit will increase. In that example, the speed would increase to 2020 RPM and the flow would reduce to roughly, in that case, from 80 to 48 liters per second, cubic per hour. So in general, you could say that the run-out flow is roughly half of the nominal flow, and the run-out speed is 1.5 to 1.8 times of the nominal flow. And the equipment what we use, the pump as turbine and the generator, all is designed to withstand that high speed and the difference in flow. So that means if a pump as turbine has run out, it has run out. It will not get disturbed. I do not require an emergency shutdown device to protect the system somehow. And this is what we use in case of drinking water plants, which I show you here. This is a unit which also has been supplied very long time ago, in 1994. It is producing 120 kilowatt. And in this application, we have the control valve, which is closing the shutdown in very long time. The closing time was elongated from 10 seconds to 20 minutes to protect the pressure side pipe, to reduce the stress on the piping. This is to prevent any water hammer. This unit is still working since 1994, and when I visited this plant 1 year ago, they said, yes, we need to go there to check how it runs 3 times a year. So all the time it's just operating. Another application here, this is showing this picture. This is a wastewater turbine. It is in Upper Austria. Behind the wood, at the horizon here, there is a paper mill, the UPM Xialei. And from this paper mill, the wastewater is supplied into the river, which is down here. This is the Traun. And they had the difficulty that the wastewater was mixed with air in their discharge pipe. So a big carpet of foam was covering the river, and they used a lot of defoaming chemicals to prevent this foam. And then they contacted us what they could do to prevent this issue, and we suggested them to use a pumpless turbine. And the pumpless turbine is situated in the small cottage. And here you see the big pipe. This is the penstock. And after the cottage, there's one big pipe and the small pipe. The small pipe is the discharge pipe of the pumpless turbine, and the big pipe is the old existing discharge pipe, which is still in use as a bypass. And the pumpless turbine is using the full head. That means from the top till the river level. So we also can use this unit, the remaining head, between the turbine axis and the river level. Another application that we have in here, this is the residual flow turbine. This was supplied in 1992 and is still in use. It's generating 75 kilowatts. It has a constant flow of 170 liters per second. This flow is required when the main turbine, which is in use only at peak hours, is shut off. So this turbine should supply enough water to the river that the fish do not get any trouble. Now another possibility are these micro power stations. At this unit, the project owner contacted us. He has some pumpless turbine in use at another power station, and he had a project where he wanted to make another power station, and the engineer suggested him to use a Pelton turbine with a vertical generator, and due to the low head of 50 meters, the turbine would have had a low speed, and then the whole unit would have been very heavy and extremely expensive. So he contacted us and said, it's not efficient. I would like to use also here pumpless turbine. And due to the big deviation of flow, this was a big challenge to us because the flow is from 100 to 500 liters per second. So we met this challenge by separating the flow into 3 different sized units. A small unit, medium-sized unit, and a big unit. In total, if all the 3 units are running, we can utilize 500 liters per second, and we generate between 38 to 198 kilowatts. So here you see some details. The line shows the run of the river flow, and below you see the reserve flow for hydrology, and then this is the usable flow for the power station. And below there you can see the cascades where we use the small unit from right lower corner. It starts to produce 38 kilowatts, then we switch to the middle unit, 66 kilowatts, then we shift to the bigger unit, and then we combine the small and the bigger, the middle and the bigger, and all the 3 units. Next possibility shows a picture that we have seen today already. These are pump turbines, where we can use pumpless turbines and pumps, or we can do some energy storage, or we can recover energy instead of throttling the energy. So the picture shows what we do here. This is an application at the German paper mill where we can do energy recovery instead of throttling. At this application, we need to have some pressure in a system where the grey water from the paper mill gets treated by compressed air to get out the printing ink from the fibers. And after this process, the pressure is still available, and this pressure is in use to run a turbine which is connected by couplings to the motor which is driving the pump. By this application, In the right-hand picture, you see the pump curve and the turbine curve. We can recover nearly 55% of all the energy which is used in this application. So first the motor needs to start the pump. So the motor size is 160 kilowatt. And when then enough water and pressure is available, this pressure helps to run the pump. And then the energy which is required to run the unit is going below 75 kilowatt. So this is another picture where we see the two units which are installed. And this customer is so satisfied that we negotiate at the moment another unit for another application. Here we see another example for some small pump storage power station. This project was in Germany, but unfortunately due to the low feed-in tariffs and some political issue, it was not realized yet. Here is a run-of-river power station, and this run-of-river power station should be used to supply power at high peak tariffs. And the low peak tariffs, they would like to use the power to do some energy storage. So they connect here a lower reservoir and an upper reservoir, and they could then pump the water up, and in high peak demand, they could use this water to run the pumps as turbines. Here we have double suction pumps as turbines. The head has some fluctuation depending on the filling level of the reservoirs, between 47 to 32 meters. The penstock length is very short, with 60 meters, and the 3 units as pumps would use 3 times 1 megawatt. Here you can see on the left-hand side the pump curve. The pump would run with variable speed to run the pump all the time at the highest efficiency point. And the right-hand picture shows the turbine curves, where we could use the turbine also in variable speed to shift the optimum efficiency point to gain the maximum efficiency out of it. This picture shows the possible layout of the powerhouse. So here we have the 3 units of the double suction pumps with the penstock and pump suction line. And then there would also be some space for another unit for later enlargement of the plant. And the whole powerhouse size would be very small, with only 12 times 21 meters. This application shows a multistage pump as a turbine. On the picture you see the unit when it is assembled and installed. This is an island power station. You can see the flywheel, which is just here to be connected to the unit. This unit was delivered 3 years ago. Some pictures about the latest projects that we realized. So in one project in the south of Austria, we replaced a very old Francis-type turbine, which was supplied in 1926 by 2 units pumps as turbine, because this was the most efficient way. By the way, the one power station that I mentioned, the micropower station is supplied to grid. The total investment cost with the pump as turbine compared with the first projected cost with the slow rotating Pelton unit, the investment cost with pump as turbine was only 1/3 compared with the real turbine. So another very interesting unit we supplied was in Germany at the fish sluice for the migration of fish upstream the river, and there they had no possibility to install a standard fish ladder because the head was too high, 12 meters. So there they used the fish sluice, which is shown on the left lower corner of this picture, and there we have the fish sluice turbine, which is a pump-less turbine. And then another micro hydropower station we supplied, where we run 4 units in parallel compared to this 1 unit with the 3 units. And then we have a drinking water turbine in Vienna at the Wienerberg, which was supplied 3 years ago. Then we have another drinking water turbines in Pretoria in South Africa at the Ande Reservoir, where we have 3 units running parallel, and these 3 units can supply power to an island power station, which is automatically synchronizing in case grid is available, and if grid gets lost, the power is supplied for internal use, for piping, corrosion protection system, and then communication system. And we also have supplied drinking water turbines to one of the 4 largest reservoirs in Seoul, in South Korea, at the Noryang Reservoir. So this was my short presentation about the use of pumps as turbines. In case you have some questions, do not hesitate to contact me. Thank you.
OK， 我们谢谢那个布鲁诺梅拉奇先生，谢谢。他也是介绍了一个泵作为水轮机的一个概念，我想也是还有很多的成功的案例，那么对我们呢也是一种启发。